We all use tools that are designed to make us faster, smarter, more efficient. And, for millions of developers right now, those tools are AI coding assistants.
Mhm.
Today, we're doing a deep dive into a stack of sources you sent us, and the core finding is, well, it's a profound irony. The technology meant to speed up development has completely redefined the security threat model.
And not in a good way.
Not in a good way at all. We're looking at a huge collective vulnerability called IDEsaster. This is the name for, what, over 30 security flaws?
Over 30, yeah. And they affect virtually every major AI development tool out there.
So our mission today is to really understand the mechanism here, because it's terrifyingly simple. It allows for data theft, for remote code execution RCE, and often without any direct user action.
And we really need to be clear about the stakes.
Yeah.
This is not theoretical. This research was spearheaded by Ari Marzouk, who goes by MaccariTA, and it highlights these systemic flaws in the most popular tools. I'm talking GitHub, Copilot, Cursor, Zed.dev, the list goes on. The finding that really shocked the security community is how it works. It's not some, zero-day bug in the AI's math. It's about weaponizing features that we've all considered completely safe, benign, even for decades, inside our IDEs.
And the industry has definitely reacted. We've seen, 24 of these 30-plus flaws have already been assigned official CVE identifiers.
That's right.
And for anyone listening who's unfamiliar, a CVE is just a standard public name for a security flaw. It's proof that this isn't just some white paper. This is a serious patched problem we all need to understand. Okay, so let's unpack that core issue then. If these IDE features like, reading a file or validating a schema, if they've been safe for years, why did they suddenly become security risks? How did developers miss this?
That is the million-dollar question. Yeah, and it's where Marzouk delivered this crucial aha moment. He basically said that the developers of these AI IDEs, they fundamentally ignored the base software. They ignored the IDE itself in their threat model.
Wait. They ignored the environment they were building the AI into? That sounds incredibly risky.
It is. They operated under this assumption that because the IDE's features, its file writers, its config editors, because they had existed safely for so long, they were inherently trustworthy. The thinking was, we'll secure the language model, and the IDE around it, well, that's fine.
So they were essentially bolting this powerful new engine onto an old trusted chassis, but they forgot that the new engine gives new dangerous capabilities to all the old parts.
Precisely. The moment you introduce an autonomous AI agent, one that can read an instruction and then just act on it without human intervention, those legacy features transform. They become, just as the researcher put it, RCE and data exfiltration primitives.
Wow.
So the vulnerability isn't in a bad line of new AI code. It's in the unsafe interaction between these agents' auto-approved actions and the IDE's uninspected existing functions.
And that explains why it affects so many tools: Cursor, Windsurf, Kiro.dev. The common thread is that combination of an autonomous agent with way too much implicit trust. Okay, so this is where we get into the actual mechanism. The IDEsaster attack isn't one thing, it's a chain reaction. It relies on stitching together 3 distinct vectors. Can you walk us through that sequence?
Absolutely. And understanding this 3-step chain is, I think, key to seeing the whole picture.
Okay.
So vector 1, context hijacking. This is the first step. It's basically a really aggressive form of prompt injection. The attacker's goal here is to get around the LLM's guardrails and trick it into doing their bidding.
And how do they do that? I mean, this isn't just typing "write me a virus" into the chat box, is it?
No, it's way sneakier. One method uses hidden characters, like invisible Unicode that get embedded in text, or a URL you paste into your IDE. A human developer reviewing a pull request won't see these instructions, but the LLM, it parses everything, and it sees those invisible characters as commands.
So the attacker fools both the human reviewer and the AI.
Right. The other method is context pollution, usually from what's called a Model Context Protocol, or MCP, server. The MCP is just how the AI pulls in outside info, like from a GitHub issue, to help it code. If an attacker can poison that external source, well, that polluted data gets fed directly into the AI's prompt. The agent is compromised before you even type a thing.
So the agent is tricked. That's vector 1. It's now under the attacker's control. What's next?
That brings us to vector 2, autonomous action. Once it's hijacked, the AI agent starts performing actions using its built-in tools. And these are legitimate tools, things like read file or write file.
Okay.
But, and this is the crucial part, in many of these IDEs, the agent does this without requiring any user approval.
So there's no pop-up saying, are you sure you want the AI to overwrite this file?
Exactly. The whole point was to make the developer experience smooth. So these tool calls were often auto-approved, especially for things inside the project workspace. The attacker just relies on that implicit trust.
Okay, and that leads us to Vector 3, which sounds like the real linchpin here.
It is. Vector 3. Feature weaponization. This is where the agent takes those auto-approved actions and abuses legitimate, trusted IDE functions to break out of the security boundary. The attacker isn't exploiting a buffer overflow, they're exploiting schema validation or settings management.
It's a complete inversion of trust. The AI uses its permissions to do something that looks benign, like writing a file, but that action triggers a latent, dangerous IDE function.
That's the perfect definition of IDEsaster. It's using prompt injection and the agent's tools to turn the IDE's own logic against the user. It is a brilliant and honestly a frightening method of compromise.
Let's ground this in reality then, because these exploit chains, they sound complex, but they are clearly working. Let's look at the specific scenarios backed by those CVEs.
Good idea.
Okay, let's start with a classic goal. Stealing data. Scenario A, data exfiltration via remote JSON schema. How does an attacker use this chain to steal, say, a .env file with API keys?
Right, so the chain starts with that context hijacking. A prompt injection tells the agent to first read the sensitive local file, the .env file, using its auto-approved internal tool, something like readfile.
So the data is now in the AI's internal memory, but it hasn't left the machine yet.
Correct. The next step is the autonomous action. The agent is then instructed to write a new JSON file using its legitimate write file tool. And here's the feature weaponization part. The attacker has crafted the content of this new JSON file to include a special line, a line that references a remote JSON schema on an attacker-controlled server.
I see where this is going. The IDE is designed to be helpful, so it sees that schema reference.
And the IDE, just doing its job, automatically makes an HTTP GNT request to the attacker's server to fetch that schema for validation. But the attacker hasn't just referenced the schema, they've embedded the contents of the stolen.env file right into the URL of that GET request, usually as a query parameter.
Wow. So the SQL data is just instantly leaked.
Instantly, during a routine auto-initiated validation check.
Wait, so the failure isn't in a feature designed for file transfer, it's in something as fundamental as schema validation. That is shockingly effective. I mean, how many times have I pasted a JSON snippet into my IDE without even thinking about it?
It's a perfect example of how a feature with no inherent networking capabilities can be tricked into exfiltrating data. And that specific vulnerability, that affected Cursor and Roo Code. That was CVE 2025-49150.
Okay, let's move to the ultimate nightmare scenario. Scenario B, remote code execution, RCE. How do we get from a hijacked prompt to running arbitrary commands on the user's machine?
This one often comes down to the agent's permission to edit configuration files within the workspace. A prompt injection tricks the AI into editing a core IDE config file, like .vscodesettings.json.
Okay.
Now, the attacker doesn't try to write a huge malicious script. No, they just change one critical executable path setting, a setting the IDE implicitly trusts. For instance, they might change the path for the PHP validator, php.validate.executable path, or maybe override the path to Git.
So the AI writes one single legitimate-looking line into a settings file, and that silently reroutes a trusted IDE function to a malicious script hidden somewhere else.
Exactly. And the next time the IDE tries to run that legitimate feature, say the PHP validator runs when you save a file, it executes the malicious script instead. And this all hinges on the agent having that default permission to auto-approve writes to in-workspace config files.
And the really insidious part is that the user doesn't even have to realize it happened right away. The payload could be delivered hours later when they trigger some totally benign action.
Right. It's a staged attack enabled by this trust chain exploitation. In this RCE scenario, this hit GitHub Copilot leading to CVE 2025-53773, as well as Zed.dev and Cursor. It really proved that any auto-approved file writing can be leveraged for full RCE.
It's a profound shift, and it brings us to a larger point. IDEsaster isn't an isolated incident, is it? It's part of a growing family of vulnerabilities that exploit this weak connection between an AI agent and the application it lives in.
We are seeing this architectural risk crop everywhere. I mean, take the flaw in the OpenAI Codex CLI. That was CVE 2025-61260. That program just implicitly trusted commands from its MCP server and executed them as startup. It's the same logic as IDEsaster.
Or Google Anti-Gravity, which used poisoned web sources to trick the Gemini agent into harvesting credentials and code from the user's IDE context.
And now we have Prompt Preempt, which targets AI agents connected to CI/CD pipelines, like GitHub Actions. By using prompt injection, attackers trick those agents into running privileged tools that leak secrets or execute code right there in the build environment.
So the risk isn't just when we're writing code, it's the entire development lifecycle. Any repo using AI for issue triage or labeling PRs is now potentially vulnerable.
Exactly. We've given these agents the ability to act, but we haven't secured the historical application features they connect to.
So what's the solution? If AI agents are the future but they weaponize our past, we need a new approach.
The paradigm that the researcher Ari Marzouk proposes is secure for AI. And I think this is the essential new mindset. It goes beyond secure by design, which is mostly about preventing bugs. Secure for AI means we have to actively anticipate how an autonomous, unpredictable AI component can abuse existing trusted features over time.
So we have to treat the AI itself as a unique part of the threat model.
A unique and powerful element, yeah, regardless of how safe the surrounding IDE looked last year.
Okay, for you listening, the learner who's using these tools every day, let's pivot to some actionable advice. How can we apply this secure for AI knowledge right now?
I think the first thing, maybe the most critical, is to treat projects as trust boundaries. Only use these AI agents with projects and files you absolutely trust. Assume any file, even a Re8m, could have a hidden payload.
And second, vet your connections. Only connect to trusted MCP servers and monitor them. A trusted server can still be breached, and if it is, that context pollution can compromise your local machine immediately.
And third, you have to be rigorous and manually review context. Scrutinize anything you paste in from a URL. Look for HTML comments, CSS hidden text, and especially those invisible Unicode characters designed to hide from human review.
What about for the people building these tools? What are the takeaways for the industry?
The recommendations are pretty clear. Tool builders have to apply the principle of least privilege to LLM tools. Only grant the absolute minimum permissions needed. If an agent needs to read the current file, it shouldn't be able to write config files.
And they must harden system prompts against injection, right?
Yeah.
Making it structurally harder for an external prompt to override the internal safety rules.
Critically, yes. And every single action the AI agent takes should be subject to sandbox execution. This limits the damage. Even if an attacker gets RCE, the malicious script shouldn't have access to your whole operating system.
And finally, a complete shift in security testing. You have to test for these things specifically in the context of AI agent interactions because the old ways clearly missed this entire class of vulnerability. So the key takeaways from this deep dive are pretty stark. IDEsaster is a massive new class of attack. The root cause is this unsafe marriage of auto-approved AI agents with legacy IDE features. And secure for AI is the essential mindset we need going forward.
And that really leaves us with a provocative thought. If our most trusted development tools, the very places where we build security for others, are this vulnerable when you add autonomous AI, what does that tell us about integrating AI agents into other safe enterprise applications? Where else might these trusted latent features be weaponized next, whether that's in finance, logistics, or HR?
That is a question we should all be mulling over as this technology matures. Thank you for joining us for this deep dive into the world of IDEsaster. Explore the principle of secure for AI further, and we will catch you next time.